So I'd like to welcome everyone to the Simulation Masterclass on integrating ExtendSim with Bayesian networks using Netica, which is a Bayesian Network software program. I have Dave Brown from Innovative Decisions with me, and he'll be doing the webinar today. So Dr. David Brown served for over 22 years with the U.S. Navy and has more than 15 years experience as a systems engineer, educator, and technical manager. A graduate of the U.S. Navy Test Pilot School and the Naval War College, he also holds a DAWIA certification in program management, systems engineering, and test and evaluation. He also has the experience in model building for Bayesian and neural networks, developing computer models generated from data sets and programming. An experienced consultant, he has successfully completed projects for ONR, the U.S. Navy, Marine Corps, and Air Force, and NASA. He has recently helped facilitate and write systems engineering policy instruction for NASA and has been a consultant in formulation and the acquisition plans of the Constellation program. Selected to an elite group, Scientists Helping America, to assist with bringing technology to bear with new war on terrorism after the 9/11 attacks. He received an ONR grant to demonstrate the shared control concept for unmanned vehicles. So with that, David, I will turn this over to you.
So good morning or good afternoon to everybody, depending, I guess, what time zone you're in. We're here in Tyson's Corner, Virginia, and I've got a couple of students that are supporting the Army right now who are taking our Bayesian Network class. And so we're going to break from class and attend the seminar here, and then we're going to work with them on building some of these integrated models this afternoon. So a little bit of background. I actually developed most of this while I was a graduate student at George Mason University, and then we found some actual uses in a number of customer applications here at Innovative Decisions Incorporated. So that's the background on this. So what I'm going to talk about for the next hour is, first of all, I'm going to describe basically how you integrate a third-party application into ExtendSim generically, because I assume that some of you, although you may be very interested in Bayesian networks, may be interested in being able to put other types of software into ExtendSim, either stuff you have written yourself or other third-party applications. And so the real trick to that is getting the mod-L code that ExtendSim is written in to talk to, in my particular case, either C or C++ programs. And there are some challenges with that, but I'll show you how that can be done. Looking at the background of those who registered for the conference, it appears that most of you, have a background in ExtendSim, but very few of you have a background in Bayesian networks. So I'm going to go ahead and explain a little bit about what a Bayesian network is and show you some examples of them so you understand what it is that we're going to integrate into the ExtendSim modeling. I'll briefly go over the ExtendSim net library, which is a set of customized blocks that allow the integration of the Bayesian networks with an ExtendSim model or simulation. And then finally, we'll wrap up with a couple of practical examples of some work. One is a project that I did for my doctorate. Another one is actually run a model in ExtendSim and show you some work that we're working on the U.S. Army right now, as they have been nice enough to allow us to show you this demo model. So specifically for interfacing Netica to ExtendSim, what I ended up doing was taking the Extend Modeling and Simulation software package, and then I had the Netica API call functions. But unfortunately, the Netica API call functions don't let me have access to the raw code. So there are certain intermediate things that I have to do before I call those functions. So I wrote a little translator, which is another DLL program. It's written in C++, C++. And basically it handles all the housekeeping details, and I'll show you some examples in code of exactly what it does. But it's an intermediate kind of glue code piece of software that sits between the Extend programming environment and the Netica API programming environment. Okay, a couple of general rules for creating or modifying blocks, and some of these are lessons learned that I learned the hard way, and other ones are things that are right out of the Extend reference manual. But the first thing is if you're going to create, modify ExtendSim blocks, you want to create a brand new, create your own new library and copy the ExtendSim blocks from the installation of the software over into that library and then work on those copies. Okay, one of the things you want to do is you don't want to mess up, the blocks that came with the software package. So keep them separated over there in a separate file because you're likely to make some mistakes and you don't want to mess up your blocks. The second thing that I learned is make sure that you use extensive error trapping so that when something goes wrong, it provides you back a message of exactly what went wrong and where it went wrong in the code. Because as you can see in this particular setup that I've got, where you've got ExtendSim calling a intermediate function, and then that function's calling a Netica API function, got 3 different levels where things can go wrong. So if something does go wrong, you need to know where in that chain it happened so that you can readily go in and fix it. And then the last thing I learned was to make sure that you use comments to readily identify within the ExtendSim block where you insert your own code, because chances are it will not work the first time. You'll have to go back and do some troubleshooting, and it's a lot easier, and where you insert the code is going to be in multiple places in the block, which I'll show you in the upcoming slides. So it makes it a whole lot easier if you really mark it easily so you can find exactly where your code is. Okay, so if you want to create or modify a block, again, assuming that you've created your own library, you've copied a block over. The way I've done it is to just look through the library and find a block that's pretty close to what it is that you want to do, and copy that over and modify it. So to modify the block, what you do is you open that block in like a modeling environment, and then you right-click on the block with your mouse and select the open structure. And you'll get the first little picture page will come up on top of the screen that has the tabs on it. If you just click on this underlined code above it, it'll go to the back. And here's an example of the code that underlies one of the blocks, function that I'm going to call procedure 5, which is abbreviated proc5. And I'm declaring that as a long function because long within ModL is used for integers. So I'm going to return an integer back when I call this function. So whatever you're getting back from the function is, whatever format that is, that's what you want to declare it as. So in my case, I'm going to return back an integer error code, and I want, so therefore I'll declare it as long. The next thing that you'll want to do is go down to the bottom of the block, which is the area where you'll find the on-init-sim. So this is the place within the block where you initialize all of your functions or variables at the very beginning of an ExtendSim program. So this is the place where you want to insert your code, where you initialize your call function. So in my particular case, I'm going to remember proc5 was the procedure that I was going to use. So I'm going to declare this function and use the command that says DLL make procedure instance, and then you see the name there in parentheses. So the name in parentheses is the actual name of the function that's in the DLL that's stored in that extensions library. So I will make, so that basically will search through the DLLs that are in your extensions. If it finds NX, then it will not generate an error, and it will initiate that to procedure 5. Okay, so the next thing then is to insert the actual code within the block for the procedure that you want to call. And I can't really give you a fast rule on that. You sort of have to look through if you're using an existing block, look through the execution and put it in the place where it most logically would execute. But here you can see that I'm going to enter a Bayesian Networks node state. And you'll notice in here that there's 3 levels of error trapping. The first thing I'm going to do is check my procedure instance and see if it's greater than 0. When I did my prior step where I instantiated that procedure 5, if it could not find the find NX function, it will set proc5 to 0. So in this particular case, if it's greater than 0, I'm going to execute the code. But if it's less than 0, if you look at the bottom of the screen, it's going to say cannot locate the set state function in my block and abort. So just like with normal ExtendSim, it'll pop up, it'll stop the program, pop up with that error message and tell you that it couldn't find this particular function in the library. Assuming that everything's installed correctly and there is no error code, then I'm going to set my node name to a variable called temp1. Node is actually the name of the variable within the block that is typed in the first screen when you open the block. And then I'm going to do another error check. I'm going to check and make sure that temp1 is not equal to nothing. So again, if there's nothing in that block, I'm going to trip an error message that says no name has been entered in the block. Again, remembering the formats have to be correct. So I'm going to call a C function. So I'm going to use the DLP to C string temp1 to change that to the correct format before I call it. So in this particular case, I checked to make sure that there's not a problem because there's nothing entered, and I positively set it to the correct C function format. My second variable is state, so I'm going to do the same error check again. I'm going to make sure that if there's nothing entered in the block, that it comes up and says there's no state entered in the block as an error. The states of the nodes are integers, so I'm going to make sure that I send it an integer. So index, which is the name of what it's going to be read out of the block, I'm going to set that to the integer value of 8 plus 0.499. So what that basically is going to do is it's going to round off any real number to its nearest integer value. And then everything in here is really error checking except for the next statement, which is the S equals DLL long C function, and then I've got my procedure 5, which is to find NX, and then I'm going to send it to 2 variables. First one is temp1, which is string converted to format. The second one is the index, and that is a number in integer format. And then the very last part of it is another error trap. When I call this function, it's going to send me back an error code. If it sends me back a positive number, then everything was good, so I'm not going to do anything else. If I get a negative number, there was an error, and depending on what, whether it was a -1, a -2, or a -3, specific error messages to tell me what step went wrong when I called my function. Okay, the translator that I spoke to earlier You can see this is the actual find NX call function. So this is, it's an external C DLL export, integer find NX. You can see I wrote this in Microsoft Visual Studio as a C++ program, and I'm calling it with my two variables. The first is character star, which is telling C++ that this is a string, and then integer f1, which is telling it that f1 is an integer. I'm going to clear all my error messages before I start, and then I'm going to basically execute 3 separate functions, doing an error check after each function. The first one is I'm going to set the name of the node that I'm going to actually set the state into. So net is a name of the network. That is a global variable in this entire program. And of course my node name is temp1 that I passed. So the first thing I'm going to do is I'm going to generate a node called node bn star that is a node named temp1 in network net. If I find that, you see I set ER equal to 1. I'm going to check for errors. If there was an error when I called that function, then I'm going to set ER to -1. And if you remember on the previous screen, ER -1 basically said I can't find the node in the network. Then I'm going to retract the findings for that node. A similar error check, but I'll set it the error to -2 if that one fails. And then finally, I'll do a set function or enter finding of the node and the state of that node, and then a final error check. If that one fails, it's -3, which said it failed to set the state correctly. And then I'll return ER. So if there were no errors, a 1 value will be returned. If there were any one of these 3 errors, it will send back that negative number, and then the mod L part within the actual block will generate the correct English text error message that will show up on the screen. Okay, finishing the modified blocks. As I mentioned earlier, you put the block on the screen in the modeling environment, right-click on it, and then open the structure. The first thing that comes up is your tabs for your dialog. So again, you can go in and modify these tabs to add specific variables that you want to input. So you can see here's an example where I'm going to open the Netica file, and so I've got a button to open the file. I've got a string in there for the file name, and then I've got another selection down there for compiling the network. One of the things that I did learn kind of the hard way as I was doing this is if you're going to modify an existing ExtendSim block, don't delete any of the input boxes that are on these pages, because if you delete it and then in the code it's looking for a variable in there, it's not going to work. You're going to get an error. So the easy way to get around that is if you don't want it visible, just use the hide function for the particular text box or whatever you want to hide, and then just move it up maybe to the upper right-hand corner or someplace out of the way. But that'll save you a lot of troubleshooting and having to go in and try to find out what code you might have to delete that goes along with that particular block. Oh, one other thing I forgot is that one of the nice things about ExtendSim is that it has a built-in help menu for each one of the blocks. And so you probably, particularly if you're going to let some other person use your block, it's a really good idea to go ahead and update that help menu so that it matches the rest of the ExtendSim library, and so they know exactly what the inputs and the outputs are, or any special things that have to go with the block. Additionally, you can see there in the upper right or upper left-hand corner there's the little icon picture, and you can change the picture to make it look like something that better represents the block that you're doing. One thing that I've done with a lot of custom blocks is go to the Microsoft library for pictures and copy and paste those in there. Those work real well. In this particular case, this is kind of the symbol for the Netica program that shows up on your desktop after you install it. So I just use the drawing tools that were in ExtendSim to redraw this little picture, and then I actually color-coded the backgrounds, as you'll see in the library, so that I could easily distinguish what type of function that these blocks did. Okay, so at this particular point, I sort of built in a part for, does anybody have any questions on how I actually developed the code for the blocks or the lessons learned or anything else before I move on into a brief explanation of the Netica software package?
I'm not seeing any questions, so I think you can move on at this point.
I'm not seeing any questions.
Okay. So if there's no questions, we'll go ahead and move on. So Netica is a separate software package. Again, it's something completely different from ExtendSim. It's made by a company called Norsys Software Corporation. And if you, that's their, to get to their website, it's www.norsys.com. And they provide a advanced Bayesian network software package that does both Bayesian networks and influence diagrams. And the nice thing about this particular product is it comes in both a graphical user interface so that you can visually build your Bayesian networks, and an application programmer interface version. And they have multiple different languages, Java, C, I can't remember all of them, but Visual Basic, to allow you to interface them into other types of software applications. But the C API is what I'm going to show you and what I use to interface Extend. Okay, so Bayesian statistics are what underlie Bayesian networks, and they work in terms of conditional probabilities. So what happens is that probabilities are updated as the result of conditions that happen on the inputs. And the nice thing about them is that the calculations can be run in either direction. So a quick example, classical statistics that I'm sure most people probably took in college. Example, you got an egg, 10 marbles in it, 8 black, 2 red. The question is, if I draw a marble, what's the probability that it's red? What's the probability that it's black? Pretty easy answer, 2 and 10 if it's red, 8 and 10 for black. So the Bayesian statistics then look at the conditional probabilities. So in this example, I've got my same bag and my same marbles in there, but now I've already drawn 3 marbles out. So now I have a condition that's been met that I've drawn 3 marbles, and that condition is that one of those marbles is red and the other 2 marbles are black. So now, based on that condition, what's the probability on the next draw that I would pull a red or a black marble? And you can see that the probabilities are different based upon the conditions that were applied. So to actually construct a Bayesian network, what we do is we create one node for each variable that we're interested in. And each node has one or more states associated with it. And these states can be either textual values, such as red and black, or they can be numeric values like 1 and 2. The nodes are then connected with arcs from one node to another node that show the relationship between the variables. And the arcs go in the direction of causal to effect. So it's a cause and effect relationship, as you'll see in the upcoming examples. So this is an example of a Bayesian network that's used in an awful lot of courses, if you ever take one on Bayesian networks. And in this particular example, it's a diagnostic network for a medical clinic that specializes in chest ailments. And you can see from the color coding on here that the top row there is my contributing factors. So these are causal relationships. The middle layer is the actual diseases. And then the bottom layer are the symptoms that are produced by these diseases. So you can see that causal effects like smoking can lead to disease such as lung cancer. And diseases like lung cancer can result in things like having an abnormal chest X-ray. So you can see the cause and effect relationships that run through the network. Now this particular network, you can see these are the baseline probabilities. There's no information that has been entered yet. So what this is telling me is that if I'm interested in lung cancer, for this particular clinic, if a person just walks into the door at random, that the probability that that person has lung cancer, given that I have no information whatsoever on them, is 5.5%. So now it's, if you go to the doctor's office, typically you check in and they give you, some type of questionnaire to fill out. So in this particular case, they had 2 questions on the questionnaire. One was, have you been to Asia in the last 6 months? And the other one was, do you smoke? And so now you can use the information from that questionnaire, and I input actual values into the top nodes. So instead of average probability, I now have actual information that this person has not visited Asia, but they are a smoker. So you can see based on that information for the lung cancer, which I'm interested in, the probability that that person has cancer has now jumped from 5.5% to 10%. So that sort of tells you right there that if you're a smoker, it doubles your probability of getting lung cancer, all other factors remaining equal. So now the person, we've taken that information, and so the people that run the doctor's office say, okay, so this person's a smoker, they have a chest problem, and they have a higher probability of lung cancer, so we send them down the hall for a chest X-ray, and they take the chest X-ray, and the tech reads it and says there's a spot on the X-ray, it's therefore an abnormal X-ray. So you can see where I put information now all the way down at the bottom as an observation of X-ray result, which is abnormal. You can see that it calculates back up through the network, and now my chance of lung cancer has jumped to almost 65%. So you can see how the calculations work in both directions. Smoking, which is a causal effect, worked down the chain to lung cancer, whereas the abnormal X-ray, which was a symptom, has gone back up to lung cancer. And we now have a new conditional probability based on the fact that we know the person's a smoker and we know the person has an abnormal X-ray. So this is a basic overview of how a diagnostic type Bayesian network would work. Okay. Each one of those nodes that you saw in the previous example has a probability table associated with it. And so if it's a parent node, in other words, it has no arcs coming into it, it's only going to have one probability for each state of the node. So in that particular case for smoking, it was, are you a smoker or are you a non-smoker? If it is a child node and it has an arc coming into it, then it will have a multiplicative table where you can see that for cancer, it has present and absent on the top, but then down the side it has one entry for each state of each one of the parent nodes that had an arc coming into it. So you can see that there's for a smoker there's a present or an absent probability, and for a non-smoker a present and absent probability. And if we had more parents, then we would have a second column that would go along with this. So instead of saying smoking, it would have something else, and it would have an entry for each combinations of states as well. So to build networks, you can build these networks either automatically or manually, and particularly with how you get the probabilities that go in. So the basic ways that you can get the probabilities that go into the table, one is to work with a subject matter expert. So if you have somebody who knows a lot about the subject, you can elicit probabilities from that person and enter those directly into the table. If you are like the chess clinic and you have a bunch of patient records, you can create like a database of those records, and you can actually use those records to have the network learn the probabilities directly, from that data. So those are the two primary ways that you get the probabilities for the networks. The third option, which is unique to this particular presentation, is if you don't have an expert and you don't have data available, but you can build a model of what it is that you're trying to do the network of, you can build an extend model and have the network learn the correct probabilities from watching the model. And I'll show you an example of that coming up. Another type of network that you can build with the Netica package is what's called an influence diagram. And an influence diagram is a Bayesian network that also contains a decision node, and it probably also contains a utility node. So the decision nodes represent the basic states that have the decision options, such as go to the store or not go to the store. And the utilities provide relative weightings, and these can be either positive or negative, that convey the relative importance of these particular inputs. So this is a simple example of an influence diagram, and you can see that we have two probability nodes, which are just like the ones that were in the previous example that I showed you. So this particular one has weather, and we're interested in whether it's going to rain or not. And based on the weather patterns, the meteorologists look at those and they make a forecast. And what we're interested in is making a decision if we go to work today whether we take our umbrella or not. So you can see that the decisions are to take the umbrella or leave it at home. And there's a utility node over to the side called satisfaction. So within the utility node, the satisfaction node, I put in the relative weighting on each one of the combinations of decisions that I can make. So you can see for this particular person, they would be least satisfied or most unhappy with the last option in that table in the case where it rains and they left their umbrella at home. So that gets a score of 0 because the person would be really wet and they would be very unhappy. The best outcome would be that if it doesn't rain and I leave my umbrella at home. That's the thing that satisfies me the most. And the other intermediate decisions are if it doesn't rain and I take my umbrella, that's a minor inconvenience. And if it rains and I take my umbrella, then that's a relatively good outcome as well. Okay. So those are the utility values that are applied to this particular decision based on the probabilities of whether it's going to rain. So here's an example of how these work. So I get up in the morning and the weather forecaster says it's cloudy. So based on this weather forecaster's prediction, if he says it's cloudy, there's about a 65% chance it will not rain that day. And so if I look at my decision based on the utility score, the leave it at home option is about twice as good as my take my umbrella option. It's satisfying my needs according to the values in the value node and the probabilities that it's actually going to rain that day. Okay, so I'll take another break right here before I go into the part to ask if there's any questions at all on Bayesian networks or influence diagrams before I move into some actual integration examples.
I'm not seeing any questions, but let's give it a moment for everyone to type it in here.
Okay.
I did have a question. If you go back a couple slides, One more. Keep going. That one. Sorry.
This one?
Yes. The decide to take the umbrella, if I sum up those percentages, or are those percentages? I've got 35
Those
and
aren't
7.
percentages. Those are satisfaction scores, so they will not equal 100%.
Oh, okay. Okay. Then I misunderstood. Thank you.
Okay. What that's basically telling me is, if right now, is if I have no information on the forecast, that based on the weather in the particular area I live and the satisfaction values, I put in my utility node that it's about 2.5 times the score that I should leave it at home.
Okay.
Because you can see from the weather that on most days it doesn't rain. It only rains like 30% of the time. But if I have some information available, like I know it's cloudy, then there's a better chance that it might rain, and therefore my take it score has risen and my leave it home score is lower. But you're correct in that's a score. It's not a percentage.
I'm not seeing any questions, so I think you can proceed.
Okay. So this is an example of the library blocks that I built to integrate the two. So this is an example of get believe, and I tried to build, use these very similar to the way Imagine That built them, with the inputs on the left and the outputs on the right. And you can see that I've modified the tabs when you open it up so that I can type in the name of the node that I'm interested in. So that's a manual entry, and then I have the option of either entering a node state or using the external connector to read in a node state from somewhere else in the block. And then on the right then is the belief, which is a probability that the node is in that particular state, is what I would retrieve. And as I mentioned earlier, when I built the blocks, I color-coded them so that I could look at the blocks and readily tell what they did. So the first row of blocks are the file functions. So those are the things like, open the program and open the file. So that'd be like, clicking on the Netica application, opening it up, and opening a file and getting it ready to use. I've also got an option if I make changes to the network to save those changes, and then like anything else, you want to close down the application when you get done with it so that you free up the memory resources once the program's quit running. Then the ones in the middle are the network functions, so if I want to compile a network or retract findings or revise probabilities, use those functions. The third row there are if I want to enter or set things into nodes, and then the last set with the light green are the blocks to retrieve information back from the Netica network. Okay. So there's some applications that we've come up with so far for customers that how you use these two packages together. So if you're a Netica builder, the things that Extend can bring to you as additional capabilities. The first one is the one we're working with the Army on, which is the ability to test a network in a simulated operating environment to make sure that it does what it's supposed to do and doesn't give you any surprises before you actually implement it in the real world. It can be used to generate the probabilities and those utility values for the tables and have the network learn all of those values from the simulation. And I've got an example coming up that I'll show you how that was done. And it actually beat a bunch of experts in how good the probabilities were. It allows you to develop networks that change over time because Netica has a function in it called fading, where things are changing. It puts more learning and more emphasis on the recent data that you give it as opposed to the old data that you give it, so it pays more attention to the more recent data. And then the other thing it does is that you can reduce the complexity of your network because when you use this thing, you can open as many Netica networks as you want to. I think, you know, it's probably only limited by the memory of your computer. And I've only got my blocks set up to do 5 at a time because I really haven't come across a application that required more than 5 networks to be open at the same time. But, you know, if you're building like a diagnostic network on an engine, I mean, you can build one network on the fuel system and maybe another network on the cooling system and another network on the oil system, and then, you know, have an overall network that looks at the health of the engine from all of these sub-networks, and have them as separate networks as opposed to trying to make one gigantic network. Okay? And then if you're extend user, the things that we found that it can help you do is, you know, unlike, you know, most of the decisions that are made within Extend, which are, you know, Boolean type decisions or, you know, less than this, go this path, you can actually feed the information that you're going to make the decision on and make a very complex multi-attribute decision which actually controls the outcome of your simulation. The network's actually controlling your simulation. The other use we found is that you know, most model building, if you're going to do an equation, you got to be able to write an equation for it. And so if you've got something that's highly complex or nonlinear, it can be extremely difficult to model. But I will show you an example of an extremely complex model that we built using a Bayes network to represent a very complex sum. Okay, so this is the primary example where I kind of try to put most of these together, and this is taken directly out of my my doctoral dissertation. But the way I did this was I built this this model, and I was actually able to get real data to build the model, so it's not made up. And so I have a radar, and this is a radar that is it's the foreign military sales version of the radar that's in the F-16 aircraft. And I have the radar cross-section measurements for a B-29 bomber. And so you can see it's a 4-part model with different pieces being modeled in different packages. The radar is, you know, there's good equations to model radar range. So I modeled that in ExtendSim. ExtendSim does very well with motion, you know, the equation of motions. So the movement of the aircraft was modeled through ExtendSim. The radar cross-section of the aircraft is highly complex, so I used a Bayesian network to model that. And then I wanted to make a decision of whether I should engage or not engage a particular aircraft based on whether it was a threat. And so I used Netica influence diagram to tell that piece. Okay. So here's the radar cross-section for the B-29 bomber, and you can see that it's kind of a real mess. If anybody out there can write an equation to generate this particular plot, please send us your resume, because we'd probably like to hire you. But if I use a Bayesian network, I can actually, you know, learn from the data, and I can actually come up with a very reasonable approximation of the radar cross-section across all 360 degrees of the aircraft. Okay. So here's some data of this F-16 radar against the B-29 bomber, and you can look at the range. It's XY direction, so it's kind of a crossing angle that I've got on the bomber. And the blue circles represent a no detection, and the green ones represent detection. And probably most of you have never operated an air-to-air radar before, but if you have, this is very much like what you see. You'll start off at max range where the aircraft's too far away, there's not enough energy, so you won't be able to see it. And then as you get in, a little closer, particularly when the aspect angle lets you see some of those bigger spikes in the radar cross-section, you'll start to get a few hits on it. But the target will fade in and out because it's going to move in and out of those spikes. And then as you get closer and closer, you'll get more and more hits on it. until you get to the point where you're getting hits almost every time, but then there are some of those really narrow areas where you get very little return because the radar cross-section is low, until you finally get in close enough that you'll get a hit every time because there's enough energy coming back. So that's very realistic of what you would see in a real air engagement. The network I initially used, I got this from a friend that I went through grad school for. He was a Navy commander, surface warfare officer, and he built this network using expert elicitation with other naval officers for the probabilities. And he actually wrote a paper on this, and I think he got like honorable mention or runner-up or some award out of it. But what he's got here is similar to the other one we looked at. He's trying to classify what type of aircraft it is and identify whether it's hostile, friendly, or neutral based on a number of attributes. So those attributes are the kinematics, how fast the airplane's going, its position in relation to where you are, and whether it is in fact on an air route, which is what most commercial airliners fly on, or if it's a military aircraft, usually they have specific return to force procedures. So if it's following those procedures, that's another attribute. Whether you're in radio communication with the aircraft, IFF is identify friend or foe. That's a transponder that's on most aircraft. So if you've ever seen like pictures of an air traffic control center, you see the radars and there's the blips, and they have little like 4-digit codes next to them. And each aircraft has an individual code. Those are the IFF returns. Any intelligence that you have on the aircraft, you may know that your enemy is basically up to the north and that there's friendlies down to the south. Electronic warfare. So if that aircraft has its radar on and it's transmitting, you can look at the pulse width, the pulse repetition rate, the frequency, etc., to identify what kind of radar it is. And then the final one is one called RSM. And RSM is basically a Doppler phenomena, where when you send your radar pulse out and it hits the moving parts of the engine of the other aircraft, there's going to be a Doppler shift. So if it's a commercial airliner and it's got one of those great big gigantic engines on it, it's going to be rotating more slowly, and you'll get a lower Doppler shift than say a fighter aircraft, a military aircraft, which has a much smaller engine, high rotating rate, and will have a higher Doppler shift. Okay, so what I did was I took George's network, and then I added a value utility as well as a decision on whether I should engage or not engage that particular aircraft on whether it was a threat. And so my options here are, it's friendly, commercial, or hostile, and then basically my decision whether to shoot or not shoot is based on, what happens if I take each one of those actions. So obviously if I shoot at a friendly or a commercial, shooting a friendly aircraft is bad, and shooting a commercial airliner is really bad. Shooting the hostile is good. Don't shoot option. If it's friendly, that's a good thing to do. If it's commercial, that's a good thing to do. However, if there's a hostile and it comes at me and I don't engage it and it shoots at me and takes me out first, that's a very bad thing to do. So this is the modification I made to George's network. So you can see that I've added in my shoot decision in the center along with my consequence node to the things that he was looking at. And then for aircraft type, I've taken the aspect angle of the aircraft and the aircraft type, and I've modeled the radar cross-section of the aircraft, which is used in the engagement scenario. Okay. So what I did was I took the model, I ran it thousands of times with random target engagements against the various different types of aircraft. I included random likelihoods that information for each node would not be available. So there was some missing information from these engagements. And I also took for each one, and I included a small number of random errors in the data as well. So, which is very real world. You know, the guy may have his IFF on, maybe it's broken, or you may have an IFF that's, you know, two targets out there, one's in front of the other, and you mistake which IFF return goes with which target. You know, those are the typical type things you see in the real world. So I took the original network, which we got the probabilities from experts, and ran a whole bunch of engagements against it. And you can see that, you know, MiG-29, I got a lot of engagements. It did very well against incoming cruise missiles. It shot at all of them. However, it also shot at a small number of commercial airliners, and it really shot down a lot of my own aircraft. So obviously there's a number of results and outcomes in here that are undesirable, and so something needs to get fixed. Okay. So in order to do that, you know, the first thing to do was look at like enemy aircraft, and typically in the military, you can only engage another aircraft if they demonstrate what's called hostile intent. Okay. So what I did was I modified the model so that I could tell in the node identity whether the electronic warfare or the radar was on and how fast the guy was going. Because for the MiG-29, if the guy's coming at me at over 500 knots and he's got a target radar on me, then he's probably hostile. If he's not, if he's just out there flying around, then he's considered neutral. Okay. So what I did was I took the entire influence diagram part of it. I took all the probabilities out, all the utility values out, and now I ran the model again. And in each case, I just made a random decision of whether to shoot or not shoot. And then I went to my utility lookup table to say, okay, I shot and it was friendly, so you know, what's my utility score? So if I shot a friendly down, I get a negative score because that's bad. If I shot a cruise missile that's coming at me, I get a high positive score because that's a good decision. Okay. So it's learning the probabilities, it's learning the utility use, so it's basically learning how to make a good decision to do that. So then I basically updated all the probabilities, and then I took that same network, or took the network, and I put it back into the simulation that I ran against George's network and ran it again. And in this particular case, you can see that in the case of the MiG-29, it's only engaging it in about a third of the cases. So I had to actually go manually review the data, and you know, only if the airplane was coming in real fast with the radar on did it engage it. Got all the cruise missiles and left alone all the commercial and friendly aircraft. So now I've got a network that has the right probabilities in it, it's got the right utility values in it, and it's ready for real-world tests, which can be very expensive. So this is an example of where, at least for within a simulation environment, learning from simulation beat a bunch of experts in determining the best probabilities for the Bayesian network. Okay, any questions on that before I run an actual model to show you that this actually does work?
I'm not seeing anything, but
okay.
let's give it a moment again. So I do have a question. Is this the library that you're working with, is this an ongoing development, or is it fairly complete in your view?
It's still ongoing because you know, there are obviously like hundreds of functions that are available within Netica, and you can see that I probably got, what, about, I don't know, 25 or 30 of them programmed. So the way it's been is that as we've tackled new projects for different customers, if new functionality was required, I created new blocks. So the library's grown quite a bit since I did my doctoral dissertation.
I'm still not seeing any questions, so you can probably proceed
right.
at this point.
So I thought you probably, you know, you can't have a master's seminar on ExtendSim without actually running an ExtendSim model to show people that it's, you know, it's not a bunch of PowerPoint slides, it actually does work. So what I have here is, again, this is from the Army, and fortunately, it's not a sensitive project, so there was no objections to me using this in a public example in this. But what the Army is doing is they're looking at using Bayesian networks to to diagnose as a prognostic tool and to actually predict engine life for some of their diesel-powered generators that we have. And so what we have here, I'll just kind of briefly go over the model, but I'm going to run this thing in, I'm using the time sync capability, but I'm going to run it in a faster mode because we don't want to sit around for like 10 minutes waiting for this thing to warm up. So from the top line here, what I'm going to do is I'm going to initialize Netica, which is basically I'm going to open up the Netica program. And then I'm going to open a particular file, which is the Bayesian network behind this. And then I'm going to delay until the end of the program, and then I'm going to close the network. Down here in my main part, what I've got going on is we're just simulating the temperature of the 4 cylinders in the diesel engine as they operate. And we're just going to, for the purposes of this demonstration, we're going to go through the warm-up mode. So I'll call up real quick the network so everybody can take a look at that. So this is the Bayesian network that we're going to use, and it extends a little bit across. But what we have here is sensors that are going to detect the temperature of the exhaust or of the gas coming out of the cylinder. We then have a node above it that is, will determine based on the temperature whether the temperature is low, nominal, or high. And then by putting all 4 nodes together, it's going to make a decision on whether, 1 cylinder is low, 2 is low, all 4 are correct, all 4 are high, or whether it's some other pattern that's out there. So that's the underlying network that's behind this model. Okay. So what we're going to do, and you use the database to capture all the data as we run the model, and then down here on the bottom is just a bunch of functions to generate the basically simulating starting about 72 degrees and then warming up to operating temperature. And so I'm going to input each one of those states into the engine. And then over on the right, I'm going to get the most likely state of the overall engine. And so at the top here, you can see here's the temperature gauges for the 4 cylinders. Here's the digital readout. Here's the input state that's going to go into each one of them. And then here at the bottom is the output of the network of overall what's the status of the engine. So it's a fairly simple model, and it's something I just built for the Army so that they could get a real good idea of how we were going to test, how we could use ExtendSim to test their Bayes nets that they're building. Okay. So if I go ahead and run this, okay, you can see the it's going to start off kind of slowly. And right now we're in a state of all 4 cylinders temperature low because we haven't reached normal operating temperature. So you can see that it's state 0, which is the lowest set of temperature readings that are in the network right now. And I added a little random variation into the temperature sensors here. So if you see them like jump up and down a little bit early, that's just that in there because obviously in the real world they're not going to all heat up at exactly the same temperature. So you can see that now we've gone to we're at state 1 because the temperature is over 100 degrees now, and we're continuing to climb. Some have gone up to 2. We're still in an overall low state for all 4 cylinders. Up to states 3 and 4 now. Okay, you notice on the graph we got a transient there where we actually went to state 8 as we went to normal operating temperature. And now I've got a fault in there where you can see that the cylinder number 4 actually ran to an overtemp condition. So it's gone to a different state of high. So it's just going to run to the conclusion here. Okay, so real quick, I'll pull up the so what we did was, as we ran that, we captured all the values for each step. I think I was doing like quarter seconds, and measuring. So you can see where it says EGT, these are the actual states of the nodes that were set. So you can see that condition 5 was the low state. And then as I went along, the interesting thing is that I get a transient here where it goes to state 9, which is an unknown state, just as the engine is transitioning between low and normal operating condition. And then it goes to 6, which is normal on all cylinders. And then one of the cylinders keeps heating up, and then it shifts to state 8, which is an overtemp condition. So one of the things we were trying to demonstrate was the fact that you can use these, if you build a good, accurate model to test these things, you can find things like transient conditions that may pop up and figure out how you're going to deal with them in the rest of your software as far as how you're going to record these operations. So that kind of concludes my presentation and demonstration, if there's any questions at all.
Have any of these models been validated against real-world systems in terms of their accuracy?
This one hasn't yet. The Army's actually got a test cell set up, and they're actually running a whole bunch of tests on their diesel engines and giving us the data on like the temperatures. So these are not the actual temperature values that are in here, but yeah, we would definitely use that data to validate it before we run the tests on the final networks.
Dave, thank you very much. Do you have any other comments before I end the session?
Nope. Thanks everybody for coming.
Okay, thank you. I get some thanks here coming in for you, so we do appreciate it. So I'll end the session now. Feel free to send me questions if you have any follow-ons or to Dave Brown at Innovative Decisions.